Okay, this paper is a good little refresher of square roots, properties of square roots. You've got simplifying just numbers, simplifying numbers and variables. You have adding and subtracting, and then you have multiplying. This was kind of the intensity of multiplying I was expecting. I would have liked some variables in there, but we will practice a few with some variables. Yesterday we started the organizer. We refreshed your memory on simplifying. With numbers, you're looking for the largest perfect square that will go into it. And you want the largest one because there could be an example like, 32. If I have the square root of 32, one person may use 4 and 8, but another person may use 16 and 2. This person's going to be done on step 2. This person is going to have to realize that 8 is actually 4 and 2 and keep going. And then they'll be done down here. Okay, so this is what happens if you don't pick the largest one. The largest one will save you steps in the end. With multiplying, if the root matches, it has to match, then you can write a multiplication of radicals under the one radical. For instance, that one. Okay, so this one, I think we finished it, didn't we? And was there room left? It was not much writing. I think it was the square root of 45, and then we wrote that into 9 times 5, and we said it's 3 square root 5, right? Okay, let's copy the more complicated one from the girl that I tutored in Florida. People say, Miss Holcombe, where do you get your money for Starbucks? Because I'm working outside working. Well, Audrey turns me. Do the roots match? What root is this one? It's a cube. What root is this one? It's a cube. So the roots match. So you can go ahead and write it as the product of 4 times 10 under just one root. You also can go ahead and multiply the coefficients. The 2 times the 6 is 12. We still have a cube root. Now we have 40. That looks a lot better, doesn't it? Now, instead of going to your perfect squares, you would go to your perfect cubes, which you need to have kind of in the top of your head or be able to generate that list. There's not a lot of room on my paper, but you could come down here and you could write like the first 5 perfect cubes. Remember, you get it by saying in your head 1 cubed, 2 cubed, 3 cubed, 4, and 5. Of course, it keeps going, but those are the most common ones. What cube from the list will go into 40? 8 will go how many times? It's the same concept as right here. You're splitting it apart. I'm going to bring the 12 down. This becomes the cube root of 8 times the cube root of 5. I split it apart. I write my cube first because it's fixing to come out of the radical, right? What is the cube root of 8? 2. So this right here is actually just 2. So now I have 12 times 2, and then the cube root of 5 comes down. So that's the answer. 24 tried that, did you get it? You had tried it? Okay, we also yesterday discussed when in the rule in math is that you absolutely cannot have a radical in the bottom of a fraction. If you are told to rationalize, it means get rid of the radical in the bottom of the fraction, which means you've got to manipulate the fraction without changing its actual value, and the only way to do that is to multiply by the number 1. So you manipulate the 1, and I think we did this one. What is the problem? The problem is the square root of 3. This is the issue, right? That's what's breaking the math rule. So you multiply by the square root of 3 over the square root of 3, because that is your fancy 1. And then you just multiply straight across. That's not a coefficient, but just a plain number with no radical times a radical is as simple as shoving them together like that. You cannot multiply the 12 into the radical with the 3 because that's not allowed. Okay? There's an understood 1 right there, and that's what the 12 multiplies by because it's not under a radical. I'll run across the bottom. You're going to generate a perfect square, which is by design. This was the goal right here. That was the goal, because now what's the square root of 9? 3. And then you have 12 square root of 3 over, that's 5 times 3, which is 15. And I think as the bell rang, I was saying that you need to be able to reduce it. That would be 4 square root of 3 over 5. The next section is if you're told to divide radical expressions. If you're told divide 2 by root 3 plus root 7, it's kind of like dividing fractions. You never actually divide. You multiply. Where's root? You're going to multiply by the conjugate. And I'm putting in parentheses because I'm running out of room. Denominator. You're multiplying by the conjugate of just the denominator. That's how you divide. You're never actually dividing anything. Okay, so refresher on conjugate. The conjugate is two terms that when multiplied by those two terms are a difference of squares. So think to your difference of squares, like x plus 1, x minus 1, right? That's a difference of squares. The conjugate is the same concept. You're going to multiply by square root 3 minus square root 7. And whatever's on the bottom, you got to put it on the top so that we're still just multiplying by a fancy what? 1. No, because you can't add or subtract radicals unless the radicand matches. And there's an example of that right here, so I'll show you that. Don't overthink it. It is exactly like when you are multiplying polynomials, because you've got like a single term times two terms. Then you've got the two terms times the two terms here, which by design are supposed to be a difference of squares, right? So remember that that's the goal. So across the top, when I multiply, I've got 2 square root 3 minus 2 square root 7. zeros, the goal is difference of squares. And I'm putting that in quotes because this is really not a polynomial. This is a radical, but it's the same concept as a difference of squares. The terms need to match, but the sign in the middle needs to be different. And that's because it's going to generate the same middle terms with opposite signs, which will then cancel. Okay, so we're going to multiply. When you're multiplying the difference of squares, do y'all recall the shortcut? No? Okay. All right, so watch. This is where the first, outer, inner, last multiplying is helpful. So square root of 3 times square root of 3 is square root of 9, which is 3. Now outer would be square root of 3 times negative square root of 7, which would be negative square root 21. Yes? Keep that in mind. Hold that right there in your pocket, right? Negative square root 21. Inner. Square root of 7 times square root of 3. Square root of 21. What did we just have? We just had negative square root 21. We just generated positive square root 21. What do those do? They cancel. That was the goal. That's why we did this. That's going to happen every single time. Every single time. If you did it right, if you put the correct conjugate, which means the same thing, change the middle sign, then that's going to happen. Now to the end. Last. Square root of 7 times negative square root of 7 would be negative square root 49, which is 7. You will notice there are no more radicals in the bottom, which is exactly what the goal was. Now you do have to clean that up though. 3 minus 7 is negative 4. Woo! It has got one more step. Just one more little step. Level up, level up. What do you notice? There's a factor of 2 in front of every radical and within the number that's in the bottom, right? There's a 2 here, here, and here. Be careful. Let me show you this. If this had been 5, you would be done. Y'all with me? Let me change my pen. If this had been negative 5, you'd be done. Okay. If this had been 8, for some reason, whatever reason, do not come in here and say, oh, divide 2, divide 2, divide 2, divide 2. Oh, that's square root of 4. Oh, that's 2. And then write that as your answer. You can't do that, okay? Whatever's in the radicand, take those marks away. Whatever is in the radicand can never be canceled with these factors that are in the coefficients and the plain number down here. Those are like apples and oranges. The radicands can only basically, if you think about it, can only do anything with more radicands. And the coefficients can only do anything with coefficients or a number that's plain and by itself. Okay? I've seen people see pretty numbers under a radical and then they just start canceling it because they saw a 2 elsewhere, and you can't do that. So be careful when you're canceling. If you got here and then canceled wrong, you would only lose half or partial credit. Okay? You would get most of the credit for getting here. This, that goes away, and this becomes negative 2. So we have the square root of 3 minus the square root of 7 over a negative 2. Now, if I gave you another dividing one, whatever the denominator is, you just change the sign of the second radical, and that's your conjugate every time. Okay? So like if you had, I don't know, of that would be square root 2 plus square root 7. Okay? What if you had that? Doesn't matter. It's still square root 2 plus square root 7. You will have a radical at the top that gets multiplied at some point, but this has nothing to do with what you're multiplying by, because that's in the top of the fraction, which is allowed. Okay? Let me give you another example of this. If you had like 12 square root 2 over the square root 6. The square root of 2 has nothing to do with the square root of 6. Like you would multiply by square root of 6 over square root of 6. Or you could write that like this, and then what is 2 divided by 6? 1 over 3, so then you could multiply by the square root of 3 over square root of 3. Multiple ways to go, like multiple ways. Adding and subtracting. Terms must be alike. This is important. Same radicand, which means same thing that's underneath. So sometimes you may not be able to do anything until they're simplified. The first example has a radical in the middle that is not simplified, and you need to get it simplified. So what I tend to do is I leave this alone, and I say to myself, like, that one's done and that one's done. This is not. This is the square root of 9 times the square root of 3, which is 3 square root 3. I go right underneath it, and I break it down. Then I bring the other crap down. So this was 8 square root 3, copy the plus, minus 2 square root 3. And now to add or subtract like radicands, it's just a matter of the coefficients. So that's 8 plus 3 minus 2. Order does matter. Remember your order of operations. Work your way from left to the right. I have seen somebody like take, oh, those are really convenient. That's 1, and then it's 8 plus 1. You can't do that. You've got to work from the left to the right because of the rule of operations. So 8 plus 3 is 11 minus 2. That one's coincidentally right. The same answer, but it doesn't always work that way. All right, look at the next one. It's a combination of adding, but then also we have a problem right here, right? And we have a simplifying. So 24's got to be broken down, and this has to be rationalized. What perfect square goes into 24? 4 and 6, so that ends up being 2 square root 6, right? Okay, I'm going to rationalize this. What do I multiply by? Square root 6 over square root 6. Multiplying straight across, I'm just going to come over here next to it. So this would give me 12 square root 6 over what? Square root 36, which is 6. What does this 6 do here? Which one does it divide into? The 12. Can it divide into the 6? No. So this goes into here, and I actually have 2 square root 6, and I no longer have a fraction. This 6 divides into that coefficient of 12 2 times. So this crap actually is 2 square root 6. I'm going to bring that back here, and then now I can write my answer.
What if that square root of 6 is next to, say, the 6 at the bottom? What does that make?
No. Well, I just rationalized it, so you won't have radical after you rationalize in the bottom. Because that's the goal. rationalizing means get rid of the radical in the bottom. Yeah.
What would you do if it didn't? If I had, like, what would you do if it was still a fraction?
You have to get a common denominator. With this is understood to be over 1. And so whatever the bottom number was, you have to multiply that. Looking at this one. So number 2 has some variables in it, which is what I was wanting you to be practicing more of. We're taking this just the square root. Now, if we were taking the cube root, oh my. Okay. I don't know why, but the pen is writing like excessively large for some reason. If we were taking the cube root of that, then you would say to yourself, you know, what cube goes into 288? And then you would take these variables and you would say, much like what you said to me when you were thinking of, was it cubes or squares? I think you said cubes. Maybe. But you say to yourself, like, how many sets of 3 could I make? And if it's x to the 4th, you can only make 1 set of 3, right? So you would pull the 1 out, but there would be 1 left over. If it was, say, y to the 9th, well, that's pretty. The cube root of y to the 9th would be y to the 3rd, right? Because there's 3 sets of 3. If it was the cube root of y to the 11th, then you break that into 3 sets would come out, and how many y's would be left? There'd be 2. Does that make sense? So don't let cube roots throw you off. Because you're cube rooting. I forgot to write. This is the cube y to the 3rd and then the cube root of y squared. You can't cube root something squared because it's not large enough. Where was the 1? Look at the one from, if you want to write this somewhere. This was a good one. I liked it. It looks really complicated. It's actually really easy. Do you see why? What do you notice about them? They're the same root, right? Which means instead of having the 2 individual roots, you could write it as 1 big root. So I could write this as 5 over 6 times the cube root of 24 over 3. And why would I want to do that? Because 24 divides by 3, yielding an 8, which is pretty. This is still 5 over 6. That 3 would divide into that 24, so it's no longer a fraction, and it would be the cube root of 8. And that's 2. You see where this is going? And so the answer is 10 over 6 or reduced 5 over 3. Now, let's look at the next one because this is a good refresher on rational exponents. And you already know this. At some point you learned this. Remember, the whole goal of chapter R was I need to make sure your algebra 2 skills are sharp so we don't end up coming to a chapter and then y'all saying, I don't remember how to do this. Because now I can say, well, we did it in chapter R, remember? Let's refresh your rational exponents rules with this example. I mean, we're just diving right into the deep end with this. Here's what you need to know. You need to put this somewhere. You need to know that the rule is, with a rational exponent, if you have the nth root of x to some power, if you have the nth root of x to some power, you can rewrite that as a rational exponent. Rational means fraction. Was that mine or yours?
I think it was yours.
Somebody paid me?
Yeah, pretty sure it was yours.
Who's paying me? Well, my watch hasn't caught up. Anyways, I'm excited. I don't know. I wasn't expecting money. The rule is, I'm going to show you how to do it. This is when I say the base, I'm talking about the x, right? That's the base. Know your vocab. The base stays the same. Because it's a radical, I can write it as a fractional exponent. Here's what goes in the fraction. The root goes in the bottom of the fraction, and the exponent goes in the top. Now, how are you going to remember this? It's stupid. Ready? Where do roots grow? In the ground. I want you to think of the bottom of the fraction as the ground, the root. And then where are exponents found? Up high, right? So this is the exponent. Okay, so looking at the rule for rewriting it, let me throw a simple one at you, and then let's go to the more time-consuming one. So, for example, if I gave you the 6th root of x cubed, and I told you to simplify it, you would rewrite it using the rules. Keep the base. You know this is going to be a fractional exponent. What's the root? Goes in the bottom. Roots grow in the ground. And what's the exponent? 3. And what do you notice about 3 over 6? That reduces to 1/2. And what is 1/2 in a fraction? In an exponent's place? The square root of x. You never write the 2, but if you think about it, go back, do the rule in reverse, right? Go in reverse. You've got the base. Because it's a fraction in the exponent, you know it's a root. What is the root of the fraction? It's a 2. We never put a 2 on a square root. Listen to the name of it. Square root. We don't ever put the 2 there. It's understood to be there. And then what's the exponent? It's a 1, which means you wouldn't write it. So if I said, here's an expression, I want you to simplify it. It means rewrite it using the rule, and then clean it up if possible, and then your final answer should have no fractional exponents. Okay? So if you stopped here, you would get partial credit. If you came here, you would get full credit. Okay? What about that one? Lots going on here. Order of operations first. Go to inside the parentheses. Do the roots match? No. So you cannot just write one big square root and multiply 125 times 5. You can't do that. Now you got to get intuitive with it. Rewrite it as a fractional exponent. So I want you to rewrite that using the rule, and then let's see if you get the same thing as me. It's going to. You want it to be as a fractional exponent first before you define the 1/3. The 1/3 is on the outside, so hold off with it until we get the inside to just one thing. So I want you to rewrite that using rational exponents. This is the rule. I was giving everyone a chance to try. Okay, 125 is raised to what power? 1/4. Root is 4. There's no exponent, so it's an understood 1. 5 is raised to what power? 1/2. Now, properties of exponents. In order to combine exponential expressions, what has to match? Starts with a B. The base has to match. I want to make a note. The base has to match before combining. When I say combining, I mean before being able to write it as just one thing raised to a power. Base has to match. This is why I like this problem. You've got to be manipulative with one of those numbers. Which one is it? 125. You need to manipulate it so that it has a base of 5. Enter a cube. What is the cube root of 125? 5. So I can rewrite that as 5 cubed. It's already raised to the 1/4 power. So when I rewrite that, here's my thought process. When I rewrite this as 5 cubed, that is already raised to the 1/4 power, then I can write it as 5 to the 3/4. Does that make sense? And I don't know, I've got to look, I've already made the test, but I'm trying to remember, this will take a while since I made it. I don't think that I might give a bonus question to this. I don't think I have one of these like as one of the questions on the test. You should be able to do this, but I don't think this is the actual, I'll look, I'll let you know. Is it test? Yes, test is B, on paper, partial credit. Give me a week to grade it, or a week and a half, there's 24 of them. But yeah. All right, I'm gonna copy this down, and it is tomorrow, so that's why we need to make sure. If you have any questions, you need to get with me, ask me. And there's no flex today, but you can text me at any given time if you have questions. Now the bases match. The rule of exponents is if I'm multiplying like bases, I add the exponents. Remember that? Like x squared times x to the 4th. And I said, think of it in expanded form. This is x times x. This is x, 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 x. So how many are there? There's 6. So this would be x to the 6. So we're going to add those exponents. You would do that in your calculator. 3/4 plus 2/4. See how I did that? 2/4. Because now they match. Would be 5/4, right? Got it right? That'd be 2/4. 3 plus 2 is 5. Yeah. in my mind, the common denominator. I thought, what's a fraction of the 4 in the bottom from 1/2, and I wanted 2/4. Now, the rule with properties of exponents is when there's only one base, and these are side by side separated by parentheses. We did this the other day. I don't remember what day it was. I said you did what with them? You multiplied. Remember that? And I said think of a simple example, if you forget, and then write it in expanded form. So that's x squared, x squared, x squared. So it's x to the 6th, because you multiply. So you multiply fractions here straight across, which would be 5/12, and that's the answer. Technically, it'd be the 12th root of 5 to the 5th power, but you know that problem's already long enough. And I remember. You already know this stuff. You just haven't used it since you learned it, probably. I was going to give you another example. What if we had 8 to the negative 5/3? And I told you to clean that up. If I said clean that up, what does the negative in the exponent mean, y'all? It means take the base and the power and move it to the opposite position of the fraction. And you might not, I'm not talking about that fraction, I'm talking about this is a solid 8 over an understood 1, but it has a negative exponent, so it means take all that and move it down. So that would leave a 1 on top, and then now you'd have a positive exponent. Once you move it, you drop the negative, because the negative's there just to move. The negative, when it's in an exponent's position, is not actually negative. It means movement. So once you move it, then you drop that negative sign because now you've moved it. You've rewritten it using the rule of exponents. Okay, so that needs to be rewritten. That is what root? Roots grow where? That's the cube root of 8 to the 5th power. That means how many 8s are in here? There's 5 of them. And I'm only taking what root? The cube root. So if you visualize to yourself, you could break that apart. If I pulled 3 over here, that would leave 2, right? So you could visualize, okay, how many sets of 3 can I make out of the 5? I can make 1 set. So it's going to come out. So the cube root of 8 cubed would be 8. And then how many would be left? The 2 behind, right? And that would be, you'd be done. And this is how I got that. This right here is 8. This just comes down. That's how I got the denominator. The rational exponents are more challenging or less challenging than rational expressions. When it was the big fraction, you had to add, subtract, multiply, or keep, change, flip, divide. Is this more difficult? Yes. It's probably because it's just you've not used it very much. If you look at your test review, there's 4 or 6, 8, 10. There's 10 practice problems that I'm looking for a root of some kind. So the root is 6, and the power is x to the 5th. And you can't go any further because it's saying how many sets of 6 can I make out of 5? You can't. So that's done. Now if that had been, let's say, 8, right? Then you could pull a set of 6 out, and then there would be 2 left over. Does that make sense? This one, it's the 5th root of x to the 1st power. You're just rewriting it. Look right here. Within the parentheses, rewrite it, then use your rules of exponents. So you would multiply. That is 7 over 1. That's why the answer is 7 over 6. And it does say to leave it in exponential form, which means you leave it, leave it up there as an exponent. I don't want it in radical form. I want to see if you know the rules of exponents. So read the directions. Don't do more than I'm asking. This one, rewrite the inside before you apply the rule, and that is a 4 over 1, which is why it's 4/5. Look at 14. That is a 2 over 1. So you multiply those straight across. They don't line up, so it looks a little confusing. But that'd be 10 over 3, which is the cube root of to the 10th power. How many sets of 3 can I make? I can pull out 3 sets, which would put me at 9, which leaves 1 behind. The test does not have 10 of these on there. The review has 10. The test is like 25 questions total. Okay, so it is proportional. It's probably 2 questions over this. 3. I'll look and I'll let you know right now. But yeah.